Hello and welcome to this Foundations of C video on functions. So just to recap on some of the theory of functions to start off. When we talk about execution in C, we're typically talking about a series of statements that execute one by one. So we might have a variable declaration, followed by an assignment to that variable, and then maybe we perform some calculation with the variable. This is a series of statements that gets executed. We go from one statement to the next to the next. We've already seen some constructs change this flow of execution though. For example, if statements and iteration constructs. In an if statement, for example, we change the flow of execution depending on a particular condition. So if the condition is true, we execute one set of statements, and if it's not, we execute another set of statements. Similarly, function calls are also a construct that modify the flow of execution. So for example, in this code we have from last time, we populate our multiplication table with values, and then when we hit this printf function call down here, the flow of execution diverts from the statements in our main function to the statements in our printf function. And just like the functions we've been calling up to this point, like printf, it turns out we can make our own functions. So if we just get rid of this code that we wrote last time, let's try and write our own function, our own named block of code, to do something. Now because functions in C are just a series of statements, you could say that we don't really need them, because in place of a function call you could just write the statements for that function. However, if we have an operation that we want to perform, and let's say we've written 100 lines of C code to do it, well if we want to do that operation twice, without functions that would mean copying and pasting 100 lines of C code. And then if we've done that, well, okay, it'll work, but then what if we want to make a change to that operation? Well, now we have to make the change in two places. And you can see how this problem would scale up if you wanted to use the piece of code, say, 10 times or 100 times. Plus, if we've copy and pasted 100 lines of C code 10 times, then the compiler is probably going to generate the instructions for those 100 lines 10 times as well. And this might make the output executable very large. And so we can solve these problems with functions. So instead of having those 100 lines scattered all over the place, we could just put them in a function, a named block of code. And then whenever we want to perform the operation, we can just call the function. So hopefully that provides some context as to why functions are useful. Now let's actually try and build one. So if we just head outside our main function here, let's try and define a function up here. And actually, you should kind of already know how to do this, because we've done it before. The main function is a function and we've written it in every program we've written thus far. And we can define other functions in the same way. So if you recall, the syntax we use for the main function is that first of all we wrote the return type of the function. So when the flow of execution returns back to where it was before a function call, we can bring back a value, just like how scanf returns an integer value that we've used in error handling before. So the first thing we do when we're writing a function is we specify the type of the return value. So the main function returns an int, typically the value 0, but the new function we're creating here could return some other kind of value. To start with, we're going to make our return type void, and this indicates to the compiler that actually we don't want this function to return a value. Next up, we have the function's name, so we can call the function whatever we like within some naming rules. So to start with, let's call our function print_hello, because we're going to make a function that prints hello to the screen. So next up in parentheses, we have our function parameters. These are the values our function requires to do its job. In this case, our function doesn't need any values to do its job, so we can just use void again like we do for main. And then we have the curly brackets, which are the body of our function. So code in here belongs to our function called printHello. So we better write some code inside of this function. Let's just have a printf. And we can printf hello. And we don't need to return any values from this function because it has the void return type. So that's our function done. We've just created a function called printHello that doesn't return a value and doesn't take any values, any parameters to do its job, that prints via printf hello to the screen. So we can call that function just like any other. If we just call it from main here, we type the function's name, so print hello, and then just some empty parentheses because it takes no parameters. There we go, we've made a function and we've called that function. So let's just call it a few more times here just for kicks, and we should probably add a new line at the end of this string. Now if we go ahead and we compile, and we run, it works just as you'd expect. So if we go back to our code here, let's modify this a bit. Let's just change this to only calling it once again. And let's make this function take a parameter. So if you recall, we have actually discussed this before. The syntax for function parameters. Essentially, you just write a comma-separated list of variable declarations within the parentheses. And these are the parameters that the function needs. So in this case, let's accept a char pointer called name, and then we can print hello and then the person's name. So we can say hello%s, and then we can just put in name. So we've now modified our function to take a char pointer parameter, and we use that parameter to output hello to that name. So we better change our function call down here. No longer does our printHello function take no parameters, it now takes a single char pointer, so we can say printHello to Sam. So this is calling the printHello function with the char pointer parameter Sam, and let's call the function again with a different parameter value, so we can say printHello to Joe. And if we go ahead and we compile that, and we run it, hello Sam, hello Joe. It works perfectly, and we're really seeing the advantage of functions. So next up, the next step, let's try and make this function return a value. So if we just clear this, let's try and make a new function this time. And let's say this one returns an int, and it's called calculate. And let's say it takes two parameters, an int a and an int b, and then we can define our function body. So maybe we return a times b plus a plus b, or something like this. So we've defined a function called calculate with an int return value that takes two integer parameters. Note that we've comma separated them. And this function returns the results of some calculation using the parameters. So let's test that out. Let's call our function down here. Let's call it a printf. So we'll printf the %d, which is the calculate of 5 and 2. So don't get confused by this. We have a function call inside a function call here. We're calling printf with a %d format specifier. And then the value we want printf to put in place of that format specifier is this expression, which is a function call to our calculate function with the parameter values 5 and 2. So a will be 5, b will be 2. And then that function is going to return a particular value, so in this case I believe it's going to be 17. So it's going to behave just like this would. So let's try that, let's save and compile and run. There we go, 17. Okay, so now you should understand how to make your own functions relatively well. I'm just going to show you now two more examples before we make something interesting. So let's just get rid of what we have so far. Let's get rid of these function calls and these function definitions. I just want to reinforce the difference here between passing values into functions and passing pointers into functions. So we're going to make two functions with the void return type. The first one is going to be called pass value, and that's going to take an int a. And the second one is going to be called pass pointer, and that's going to take an integer pointer a. And then in the body of pass value, we're just going to set a to 5 and then printf the value of a. And then in pass pointer, we're going to do the same thing but through the pointer. So we're going to say dereference a equals 5 and then printf our integer dereference a. And let's just make it clear in the text we output where the text is coming from. So let's just say, okay, pass value d and pass pointer d. Now some of you may be thinking that these functions will do exactly the same thing. And you're kind of right, but you're kind of wrong. So if we just declare two local variables to main, if we have an int a and b local to our main function, and let's initialize these both to 10. So note that the a in our main function here is totally different from the a in the other functions. So we know the variables both start at 10, and then what we're going to do is we're going to call pass value with a, and we're going to call pass pointer with the address of b. Because obviously we can't just pass in b in this case, because b is just an integer, not an integer pointer. So we need to pass in the address of b. And then all we're going to do is we're just going to have some printfs, the printf the value of a now, and the value of b now. And before I run this, I'd like you to just predict what values you think are going to get output. So we declare some local integer variables in our main function. We call them a and b and initialize them both to 10. We then call pass value with the parameter a, and then we call pass pointer with the parameter the address of b, and then we output our values of a and of b. So let's try it. If I just compile and run. Okay, so we can see what happens in pass value. Its parameter a will start off with the value 10, because we called the function with the value of the a variable local to the main function. We then assign its parameter of a local integer variable a the value 5, and then we printf that value and the function's over. So we return to main, and then we have our function call to pass pointer. We pass it the memory address of our local variable b. And so inside pass pointer, our integer pointer parameter a is going to be set to the memory address of the local variable b in the main function. We then dereference that pointer and set it to the value 5, and because we're writing through that pointer, that's going to set the local variable b in main to the value 5, and then we printf, quite obviously, pass pointer 5. Then we return back to the main function, we printf the values of a and b after those function calls, and we can see that a is still 10, but because we passed the pass pointer function the memory address of our variable b, and it wrote through that memory address, the value of our local variable b is now 5. It's changed from the value 10 to the value 5. So just like how we pass in the memory address of variables to scanf to let it change the value of the variable, pass pointer is a function with a side effect. It modified our local variable b. So I hope that demonstrates the difference between passing values into functions and passing pointers into functions. And for anyone still not sure about this, I'm just going to quickly step through it in the debugger. So if we just switch over to Xcode and I hit run, you can see down the bottom here, a and b start uninitialized. So let's step through. They're now both initialized to 10. Then we call the function pass value. Okay, so we've diverted the flow of execution. We're now inside of that function. So you can see a is currently set to 10 because that's the parameter we passed in. We then assign that variable a, and this is the parameter variable a that is local to the function, the value 5. And then we have our printf call, and we return back to our main function. And then we have our pass pointer function call. And we're now in the pass pointer function, and you can see the local integer pointer a in here has been set to a particular memory address, which will be the memory address that got passed to the function, the memory address of the variable b in main. We then assign through that pointer the value 5, so we should be able to see here if I just add the expression dereference a, The dereference of a is now equal to 5 when previously it will have been equal to 10. We then have our printf, and we return to the main function. And now you can see here a is now 10, b is now 5. So there we go. Hopefully that should explain the important difference between passing values and passing pointers. So one last thing to end this video, let's try and make something interesting. So if we just get rid of our function calls and our function definitions. Some writers like writing with particular constraints. Famously, for example, Dr. Seuss wrote green eggs and ham using a vocabulary of only 50 different words. With a list of these words, we're going to try and write a program that reads a sentence and checks if it uses only this vocabulary of words. So first of all, let's get our list. And I'm just going to paste our list up here, because this way it'll be accessible to all the functions we write. So this is just an array of char pointers called valid words with a particularly long list of constant strings to initialize the array. So now if we go back to our main function, let's make a plan for how we're actually going to do this. So there are a number of different ways you could go about this, and if you're feeling up to it, try doing it on your own. But my plan, and thus the way we're going to be doing it in this video, is we're going to read the input sentence character by character, and we'll read each character into some array buffer, and then if we encounter a space or something like that as the next character, we can deal with that word, strip away punctuation, and then check if the word is or is not in our dictionary of valid words. So this is quite a big task compared to the things we've made thus far, and we are going to make a function to make the code a little cleaner, but I'm going to walk you through it, so try not to worry about it. So first off for this plan, we're going to need an array of chars to store words. So let's do that. We're going to make a char array called word buffer, and it's going to be 512 items long. So each word we're processing in the sentence is going to go through this array. But because arrays in C have a fixed size, we're just going to say we can't accept words longer than 512 characters in length. So next up, because we're doing things character by character, we're going to need some variable to track what character element in our array we want to write next. So we'll make this an integer variable and we'll call it cursor, and it can be initialized to the value 0, because we want to start writing words character by character into our word buffer from the index 0. Next up, we're going to need a loop to repeatedly get characters from the user. So let's make this a while loop, and let's make our condition while the word buffer isn't full. So because we're going to be using cursor to track what we're writing in the word buffer, we can use the condition cursor is less than size of word buffer. So size of is going to give us the size of the array in bytes, and because it's a char array and chars always have a size of 1 byte, that's going to be the same as the length of our array. So it's the same as writing while cursor is less than 512. So what do we want to do inside this loop? Well, first of all, let's get a character from the user. So to store this, let's make a char variable called ch, and we're going to initialize that to the result of the function called getChar. GetChar is a C standard library function that gets a character from standard in. So it's a bit like scanf, but only for a single character. So now that we have a character from the user, well, our course of action is going to depend on what the character value is. This is perfect grounds for an if statement. So we're going to want to do something different if the character is a new line character, or if the character is a space, or indeed if the character is a hyphen, because that's really a lot like a space. Otherwise though, the normal course of action will be to set the word buffer element with index cursor to our character. And because we've written to this element, we then want to add 1 to our cursor. So the next element we write is in the next slot. And we could actually do this in one line if you really wanted. We could actually move the increment here, and that would work as you would expect, but let's just keep the clarity for now. Okay, so the loop should now populate our word buffer when we have a character that isn't a new line, space, or hyphen. Now let's deal with the case where we do have one of these strange characters. Well, if we're going to be dealing with the word buffer like it's a string, the first thing we're going to want to do is null terminate that string. So we can do that, we can just say the word buffer at index cursor is equal to the null character. So after we've done that, we're going to want some kind of checking on this word. We want to check if the word is in our dictionary of valid words, but we'll do that in just a second. Let's just deal with the remaining logic of this for now. So if the character is indeed a new line, we have a special case for this, because if it's a new line, our sentence is over, so we can break out of the while loop, and then in the remaining cases, so if we've encountered a space or a hyphen, we want to reset our cursor to 0, because we've already processed this word, and we want the next word to populate our word buffer from index 0. So now we actually need to process the word. Well, this is kind of a modular check that we might want to do elsewhere in a program that's dealing with these kinds of things. So we're going to factor this out into a function. Let's write the function call and then the function definition. So let's call the function word meets constraints, and we'll just pass it in the word buffer. And now we ought to define that function, so let's do so up here. And let's just make it have no return value for now. Word meets constraints, it should take a char array word. And for the time being, let's just printf the word to see if the code we've written so far works okay. So word. Because our word buffer is null terminated, this should work just fine, presuming we've written the code in main correctly. So let's test this out, let's compile, and run, and okay, we need to enter a sentence, let's try that. This is a sentence, and awesome, we get the output we would expect. Each word resulted in a separate function called the word meets constraints. Okay, so things are working so far, let's try the next step. First of all, word meets constraints is definitely going to need to return a value, so let's make it return an integer value. And for now, let's just say it returns 1. We're not going to code the checking quite yet, so we're just going to say the check always passes for now. So now that word meets constraints returns a value, we can do some checking in main to see if all the words meet the constraints. So let's create another integer variable in main called metConstraints, and this can be initialized to the value 1. We're going to assume at the start that all constraints have been met, and then in checking each word, if we find one that does not meet the constraints, we'll set metConstraints to 0. So let's deal with that logic now. If we go down here, we can say if the word does not meet the constraints. So because word meets constraints returns a 1 or 0 true or false value, we can use the logical not operator to negate that, and so in the case that we don't meet the constraints, we want to set metConstraints to the value 0. And because we no longer need to process any more words, we know we have not met the constraints, we can just break out of our while loop as well. With this constraint status flag being set as appropriate, we can have a conditional down here at the end after our loop that says, okay, if we've met the constraints, do one thing, otherwise do some other thing. So we probably just want some printfs here. We can say printf, the input sentence met the specified constraints. Or in the case where we don't meet the constraints, we can have a printf that says, did not meet the specified constraints. So let's test what we have so far. If we compile and run, and let's put this in as our sentence. Do you like green eggs and ham? I do not like them, Sam, I am. This is some content from green eggs and ham, so it should pass our validation usually, but it should definitely pass anyway because word meets constraints just returns 1 right now. So let's see what happens. Okay, so I've missed a new line off of our result message, that's fine, I'll fix that in a second. We can also see though that we're getting punctuation included in our words, which isn't good because the words aren't going to have the punctuation on them in the valid words dictionary. On the plus side though, it looks like our hyphen support is working just fine. The hyphenated Sam I am resulted in 3 word meets constraints function calls. Let's just try and fix those problems I outlined though. So first off we have the new lines. Let's add those in. Now our punctuation issue. So this is actually a very simple fix. Instead of having this else here, we can change this to an else if, such that we don't have to accept particular characters into our word buffer. So in this case we can say, well, else if the character can't be a comma, and the character can't be a dot, and the character can't be a question mark. And realistically there might be other things you want to skip here too, but we'll just keep it as this for now. So let's test this again. If we go back and we compile and we run and we put in the sentence we did before. There we go, that looks much better. The words are now pretty much how we want them to be. We might have some capitalization issues too, but we're not going to deal with those in our version of the program. You're welcome to try and address these issues in your own version. So all we really need to do now is actually set up the word meets constraints function such that it actually checks our valid words array. So let's do so. It's not actually that difficult, so let's get rid of our printf and our return in here. Oops. And all we're going to do is loop through each item in our valid words array, and for each item, if that string is equal to the string we've been passed, then we return 1. The word has met the constraints in the dictionary. Otherwise, if none of the words match, we return 0. So we can just use a for loop to iterate through the array here. We can say for int I equals 0, and while I is less than, well, we want to go through the entire array, so we can do this trick with size of valid words over size of valid words 0. So that's going to be the length of our valid words array, because we get the size in bytes of the whole array, and we divide it by the size of one element in the array. And then for our update, we want to plus I. So this should iterate from I equals 0 to I equals whatever the maximum index in the valid words array is. So we can just do a string compare of valid words I against word. So we can say if the string compare between word and valid words I is successful, then we return 1. I think we've covered this string compare function in the past, apologies if we haven't. This is a C standard library function with a prototype in string.h, and it returns 0 on a successful match, so we're using the logical not operator to return 1 from our function if there is a match, and otherwise if we just end up out of this loop, we can just return 0. And I guess for debugging purposes, let's just put a printf in here as well. Failed to match word, %s, and then we want the actual string word. So I see no reason why this shouldn't work. Actually, we should also probably handle the case down here if we do indeed encounter a word too long for our word buffer. So maybe we'll switch these cases around. We can say, actually this one is here, this one is here, and then we can say if not met constraints, or if the cursor is equal to the size of the word buffer. So now we make sure we go to the fail case if a word is too long. So this is as far as we're going to take this program. Let's just test it out first though. If we just compile, and we run, and we paste in our sentence, and I've removed some capitalization because our program doesn't account for that at the moment. And okay, we met the constraints, that's great. Indeed we should. And let's try again. This time with a sentence that should fail validation, so Sam I source crunch failed to match word source crunch. The input sentence did not meet the specified constraints. So that is our program finished, and indeed the end of this video. There are quite a few components to this code, so I hope you understand it. If you don't, try stepping through it line by line. We read words into the word buffer character by character, and then process the words to check if they've met the constraints. As a challenge to those that want to go further with this, first of all try dealing with the uppercase lowercase thing. Maybe you could define a function to help you with that. And if you really want to stretch yourself, try making the program accept an arbitrary list of words to check against. So that is the end of this video. I will see you next time.